Welcome to Demystifying Math. In this lesson we're going to be discussing derivatives. Let's start off with a revenue example. Suppose that we have the revenue for a product is given by 16x minus x squared, where x is the number of units sold. Let's try to graph our equation. Let's first try to find our x-intercepts, or the zeros of the graph, or in other words, where the revenue is equal to 0. So replacing r of x with 0, and then factoring, and then setting each factor equal to 0, we can get our x-intercepts at 0 and 16. Let's also try to find the vertex. Now, in this case, when we're trying to find the vertex, that means that we want to find the number of units sold that gives us the greatest possible revenue. So, since it is a parabola or a quadratic equation, in order to find the vertex, we can use negative b over 2a, which gives us out 8. Now you could have also used symmetry to find your vertex because you have your two x-intercepts at 0 and 16. So your vertex, the x value of vertex, will be halfway in between those 2 points. Okay, so now that we found that the x-coordinate is 8 for our vertex, let's go ahead and plug it into our revenue equation, and we get out 64. So our vertex is at the ordered pair 8 and 64. Okay, so now we should be able to graph it. We also know that our parabola opens down because we have our leading term has a negative in front of it. So now we were able to graph it. Now that we've graphed it, let's decide what its domain is. Well, when we're looking at the graph, normally we'd say the domain is all reals. But since this is representing revenue and number of units sold, it doesn't really make sense for either one of those things to be negatives. So we're going to restrict our domain to be between 0 and 16. And now what we want to do is figure out what our range is. Well, the range is going to be from the lowest point to the highest. Since we've restricted the domain to start at 0, our lowest value is 0, and our highest is where we have our vertex at 64. Now, this graph is curved. It's not a straight line. So the slope is not constant. What we want to decide is on what interval it is positive slope and what interval it has a negative slope. So if we look to the left side of the vertex, you can see that it's an increasing part of the function. So that's where the slope would be positive, from x values of 0 to 8. So what on an interval is the slope negative? Well, it's going to be on the right side of the vertex, so going from 8 to 16. Now, when we talk about slope, we're talking about the change in y over the change in x, or the change in our output divided by the change in our input. So that's going to give us actually a unit of measurement in this case, because on our y-axis, we're really plotting the revenue, and on our x-axis, we're plotting the number of units sold. So our slope is really giving us revenue per unit. Okay, so let's try to find out what that average rate of change is, going from 2 units to 5 units. So I've drawn a secant line going from x equals 2 to x equals 5 on the graph. And what we want to do is to find our slope of that secant line. So the first thing that we need to do is plug in our two x values. So evaluating the revenue function at 2, we get out 28. Evaluating the revenue function at 5, we get out 55. So now we're just going to do our slope formula and figure out what the slope is. So the slope of that secant line is 9. Notice that right before we got 9, we had 27 over 3, which means that for the 3 units going from 2 to 5 units sold, we increased our income by $27, which means that on average there's a $9 increase in revenue per unit between 2 and 5 units sold. Now, sometimes what we want to do is find the marginal revenue, or the change in the revenue, at exactly a specific point. Let's say that we wanted to find it at exactly 2 units. This would be called an instantaneous rate of change. And in order to find the instantaneous rate of change, what we need to do is take the distance between the 2 points, like we had between 2 and 5, and close them together so that the distance between the 2 points is almost 0. Okay, so here's what we had before. We had these 2 points, A is at 2 and B is at 5, and we found that our slope is 9. What we now want to do is find the slope when the distance between A and B is virtually 0. So we're going to take this point B and we're going to bring it in closer to point A. Now what you should notice is that the slope of the secant line is getting steeper, but at the same time as points A and B come closer and closer together, it's not going to be a secant anymore. It's going to be a tangent line. And what we want to do is find the slope of the tangent line at x equals 2. Okay, so normally we use x1, y1, and x2, y2 for our 2 ordered pairs. But what we want to do here is express the x1 as x and the x2 as x plus this small amount, which is delta x. So this delta x is what we want to approach 0. So we're going to do a limit formula to help us do that. So we want that distance between the 2 points, which is delta x, to close in on 0. So that means our ordered pairs can be written in terms of function notation, where we have x and the function evaluated at x. And for our second point, we have x plus a little bit more, which is the delta x, and then f of x plus delta x. Now what we can do is just plug those ordered pairs into our slope formula and simplify a little bit. So where we had y2, we're going to replace it with f of x plus delta x. And where we have y1, we're going to replace it with f of x. And then we did the same thing in the denominator here. The only difference is that in the denominator, the x and the negative x canceled each other. So we simplified down to this formula. And this formula is really a slope formula, but we call it the difference quotient. Now since we need the delta x to approach 0, we're going to take the limit of that difference quotient as delta x goes to 0. And that's going to give us a formula to find the slope of the tangent line. Okay, so our formula in this case, our equation was r of x equals 16x minus x squared. And what we want to do is plug that into that difference quotient. So the first thing that we're going to do is take our function and replace x with x plus delta x. So we did that here. And then it says minus the f of x function, which in this case is our r of x function, and divided by delta x. Now we have to expand everything out. So what I did was I distributed this 16 here and here. And then this is a binomial, so any binomials have to be FOILed out. So I FOILed that out. And then over here I just distributed the negative. And now I'm going to distribute this negative to these 3 terms and then simplify it a little bit further. Now that we're at this point, you should be able to see that the 16x and the negative x canceled with these 2 terms at the end. So we're left with this. And now what you should notice is that everything here has a delta x in it. So we can divide out that delta x. And we're left with just 16x minus 2x minus delta x. Now our next step is to take the limit of the function as delta x goes to 0. So our third term here is going to go to 0. Everything else will stay the same. And we're left with 16 minus 2x as our derivative, which again is the formula to find the slope of the tangent line at a specific value of x. So in our particular problem, we're looking for x to be 2. So we're just going to take our derivative formula and plug in a 2 for x. And we get out 12, which is what we saw a few minutes ago on the graph. So our instantaneous rate of change at x equals 2 is 12. And this is what we call the marginal revenue, which means that for sales of 2 units, there is an increase of $12 per unit. So on our next slide, we're going to do some more with the derivatives and using this limit definition to find the derivatives. Thank you for tuning in to Demystifying Math.